So in this chapter, we'll be discussing about the basic magnetic properties of materials. Okay. And then we will also talk about bar magnets, their behavior, how they can be compared to electric dipoles. Okay. Like bar magnet is a magnetic dipole. It has a north pole and a south pole. You can compare it to an electric dipole. You can find out its magnetic field, magnetic moment, and such things. Okay. So tell me, someone is asking, is this chapter important for JE? Very, very important. Okay. Why I say that is because, as I said, in this chapter, you'll be learning about the magnetic properties of materials. Sometimes they will ask you direct questions from this chapter, but sometimes they'll ask you indirect questions. Like they can mix moving charges and magnetism and this chapter. See, whatever we learned in moving charges and magnetism, we took vacuum as the medium. We always used mu naught. We never considered any other medium. Okay. In this chapter, you will learn what to do if there is some other medium. And then they can ask you questions by combining both. Like they can say, there is a soft iron core inside a solenoid. How much magnetic field does it produce? And in the next chapter also, this is important. Electromagnetic induction. You learn something called inductance of a solenoid and all. Okay, solenoid or loop that changes from medium to medium. Like in electrostatics, we had learned about this device called capacitor. Can one of you quickly tell me on what factors capacitance of a capacitor depends?
So the space between the plates and geometry of them.
Not, you should not, okay, don't say space, you should say medium between the plates. Okay.
Yes.
With what the space is filled, it depends on that. Similarly, in the next chapter, electromagnetic induction, you will learn about a device called inductor. Okay, some of you may have learned already. Inductance of an inductor depends on the shape and medium. Okay, and inductor stores magnetic energy. Capacitor stores electrical energy. Inductor stores magnetic energy. There it depends on medium to medium, it will change. So how to include the medium factor in the equations you will learn in this chapter. Okay, so one of you quickly tell me how, like, magnets are found in nature. Okay, how do they exhibit magnetism? What gives them that property? Like what forms a north pole and a south pole in an object? Basically at the fundamental level. We had discussed this briefly in the beginning of the last chapter. Okay. What is the smallest unit of matter? Atom. What does an atom consist?
Protons, neutrons, electrons.
Protons, neutrons, electrons. How are they arranged?
There are protons and neutrons in the core of the atom, and then electrons on like the orbiting them.
What is that core called?
Nucleus.
Nucleus. Okay. Protons and neutrons are tightly packed in the nucleus of the atom, and electrons revolve around the nucleus in orbits. Okay. So basically the nucleus is positively charged and negatively charged electrons revolve around it. Okay. Now you consider a stationary atom. It is possible for atoms to be stationary. I mean, not perfectly stationary. An atom will come to absolute rest only at 0 Kelvin temperature, at the absolute zero of temperature. At any non-zero temperature, atoms will be vibrating. That's fine. But their mean position will be fixed. They'll be vibrating about a mean position in a solid. Okay. Electron will be revolving around the nucleus. Electron is a charged particle. Charge is moving. So it's like current flowing in this orbit. Okay. Suppose the electron moves this way. Negative charge moving clockwise means current flowing anti-clockwise. So it's like there is a current in this loop. Now charge of an electron, the magnitude is E. Let's say it is moving with a speed v. Assume the orbit radius is r. Can one of you quickly tell me how much current is present in this orbit on average? If an electron having magnitude of charge E moves with a speed v in an orbit of radius r, how much current exists in that orbit on average? What is the basic formula for current? Or average
Q by
current?
C.
Charge divided by time. Correct. Yeah, in the meantime, you can derive the current in this loop. As someone was saying, average current by definition is charge divided by time. The charge revolving in this orbit is the charge of the electron. So E, after how much time will that charge pass through each point? Okay. So for instance, the electron at this moment is at this position. Okay. So through the cross section there, or through that point, there is a charge E passing. Now the electron has to complete the revolution and come back to that point. To complete the revolution and come back to that point, it takes a time period of revolution, that is 2 pi r by v. And in that much time, a charge E passes through that point. Or after every interval of that much time, charge E passes through that point. Therefore, the current in this loop is EV by 2 pi r. Some of you have given answers, but okay. It's EV by 2 pi r. Okay. So this orbit in which the electron is revolving, what does it now behave like? The orbit in which the electron is revolving, what will it effectively behave like? It's a current. It's a current loop. Okay, that means it is a magnetic dipole. So in this case itself, you tell me electron is revolving clockwise, so current is anti-clockwise. Which side of this loop is the north pole and which side is the south? Just a minute, I'll switch back to Wi-Fi. 1 second. Yeah. Which side of this loop is the north pole and which side is the south pole? Are you all getting me?
Yes, sir.
Okay. You know how the current is flowing. Tell me which side is north, which side is south.
But towards us, it's north, and into the screen, it is south.
You just have to curl your right hand fingers along the flow of current. You do that. Flow of current is anti-clockwise. Curl your right hand fingers anti-clockwise. You'll see the thumb pointing towards yourself. So out of the screen is the north pole and behind the screen will be a south pole. Okay. So every revolving electron in every atom produces a magnetic field. Fine. There is no electron which does not do this. And this is what gives rise to magnetism in materials. Okay. Does every material like plastic, steel, wood, does every material have electrons revolving around the nucleus or not? What do you say? Okay, there was some interruption once again. Are you all able to see my screen?
Yes, sir.
Right. So yeah, answer my question. Does every material have electrons revolving around the nucleus inside them or not?
Yes.
Yes. Then why does every material not behave as a magnet?
Sir, like I don't know the reason, but they say that the special arrangement of atoms do it.
Who
Like
says?
they behave.
Who said?
Like once I read some.
But try to think, no? Others also try to come up with an explanation. If every material has electrons revolving around it, why does every material not behave as a magnet? Any idea?
Sir, is it like the magnetic field will get cancelled?
Someone else was saying something.
In chemistry, they say like if there are no unpaired electrons, the material becomes diamagnetic.
If there are no unpaired electrons,
The material becomes diamagnetic, non-magnetic.
if there are no unpaired electrons, it is diamagnetic, correct? What does that term unpaired electrons mean? Okay, listen. Yeah, what Yash said is correct. Each electron produces a magnetic field, but it's not necessary that every electron in the material, in fact, in a single atom also, it's not necessary that every electron revolves in the same manner. Now, hydrogen has only one electron. It will revolve whichever way it revolves, that's fine. But all other atoms, all other elements, they have more than one electron in their neutral state. It's not compulsory that all the electrons in a material revolve in the same manner. Okay, so suppose there is one electron revolving clockwise like this, and in the same atom there is another electron revolving anti-clockwise at the same rate. Then what will happen? The magnetic field produced by this electron will get cancelled by the magnetic field produced by that electron. That, see, from whatever chemistry I understand, that is what they mean by pairing of electrons. Okay, so if there are no unpaired electrons, means all electrons are paired. What does that mean? For every electron, there is another electron cancelling its field. Okay, then we say all the electrons are paired. In that case, net magnetism of the atom will be zero. Net magnetism in the material also will be zero. Definitely, at the atomic level itself, if it's not a magnet, then in the material level also it won't be a magnet. Okay, so I think that is why if unpaired electrons are not there, it is what is dia, para, ferro, that we will discuss in a short while. So did you all understand how magnetism arises and why every material does not behave as a magnet? Any doubts in this? Okay. Now, as someone was saying, in some materials, the magnetic field produced by every electron is cancelled at the atomic level itself. Fine. In some materials, it may not be cancelled. At the atomic level, it may not be cancelled. Okay. For example, you take hydrogen itself. Hydrogen only has one electron in the atom. Then there is no other electron to cancel its magnetic field. So each hydrogen atom produces a small magnetic field. Very small magnetic field, of course, but it does. But you take a bunch of hydrogen atoms together. Okay, not bunch. You take a millions of hydrogen atoms together. Each hydrogen atom is a dipole. That's fine. But if you put millions of hydrogen atoms together, will they all align themselves in the same manner, or will they be aligned randomly? You put millions of atoms together, will they all automatically align themselves in the same manner, or will they be aligned randomly? Now, especially, see, hydrogen is a gas. In a gas, there is definitely randomness. You can never dictate gas atoms or gas molecules to be in a particular place. They will be moving around randomly. They will be rotating also. Fine. So we are taking the example of hydrogen. In hydrogen, definitely at the atomic level, there is magnetism because there's only one electron. Its magnetic field is not cancelled. But if you take a certain amount of hydrogen, there will be millions, trillions of hydrogen atoms in it, maybe much more than that actually. Okay. So many hydrogen atoms put together, they are all dipoles, but they are aligned in random orientations. So net dipole moment of the entire material can become zero. At the atomic level, they are dipoles. But at the object level, if you see, or at the system level, if you see, the net dipole moment disappears. That possibility is there. Okay. So why all materials don't exhibit magnetism is because some of them don't have magnetism at the atomic level. Some of them have magnetism at the atomic level, but at the object level or the system level, their dipole moments are all cancelled. So the object as a whole doesn't behave as a dipole, doesn't behave as a magnet. That possibility is there. For some rare materials, at the atomic level, it's not cancelled. At the system level also, it's not cancelled. Such materials actually behave as magnets. Okay, but they are very rare, as you know. Okay. Now, a non-magnetic material also, okay, or a material which is normally not a magnet, can be magnetized. Fine. Let's see how that can be done. Any idea? How are magnets made? Or how can we magnetize a material?
By passing current through it.
No,
So like electromagnet.
that is electromagnet. That is not at the material level. Current is producing the magnetism. Material is not producing. Okay, listen all of you. There is one idea that we can use. You think of electric dipoles itself. I think we had discussed, we had discussed this when we talked about insulators or dielectrics. In an insulator, okay, consider it is, assume it is polar. There will be dipoles randomly arranged like this in a polar dielectric. Okay, they are randomly aligned. But if you switch on an electric field towards right, what will happen to all these dipoles? These are all electric dipoles. We are talking about electric field, electric dipoles. Suppose you switch on an electric field towards right. What will it do to these dipoles?
They will get aligned in the direction.
They'll tend to get aligned in the direction of electric field. So you'll see a little bit of rotation. There may not be perfect 100% alignment, but more or less they will all be tilted towards the direction of the electric field. So slightly tilted to the right. This will be the situation. Now in the original system, since the dipoles were randomly aligned, the net dipole moment of the system, dipole moment is a vector quantity, net dipole moment would be 0. But in this system, in the second one, where the electric field aligns the dipoles in a particular manner, the positive charges face this side, negative charges face this side. So effectively, there is a net dipole moment this way. Okay, something similar happens in magnets also. Not exactly the same. We'll discuss in detail, but this is how you can magnetize a material. So basically what we do is we switch on an external field, that's all. Okay, once you switch on the external field, some changes will happen inside and the material will get magnetized. Okay, that is the basic idea behind magnetizing a material. Okay. Listen. So when you want to magnetize a material, we place it, or you need to place it in an external magnetic field. Fine. Now, this external magnetic field divided by mu naught. This quantity is called magnetizing intensity. This is called H. Sorry. Okay, it is defined as a vector quantity called magnetizing intensity. Okay, basically it tells you about how strongly we are trying to magnetize the material. Okay, it is related to the strength of the external field. You need to remember this definition, all of you. Magnetizing intensity. Okay. So with what intensity we are trying to magnetize the material. Okay, so obviously this should be related to the external magnetic field that we have applied, and it's a vector quantity. It has the same direction as the external field. Okay, solve this, all of you. Derive the dimensional formula of magnetizing intensity. Dimensional formula and SI unit also. What happened? Why is it taking so long? I got one answer as L power minus 2 A square. I got one answer as M L power minus 1. Okay, A power minus 1 T power minus 2 L. I don't think it will be that complicated. Okay, yes, just tell me, how did you try to derive the dimensions?
Sir, first I derived the formula of magnetic field, then I divided it by mu naught.
You remember mu
Like
naught
that is the
dimensions?
formula of mu.
You remember the dimensions of mu naught?
No, sir, I was deriving.
Okay, you wasted time. Okay, that is a useless approach. I mean, lengthy approach. Okay, Rishi, how are you trying to derive the dimensions?
Sir, I took the dimensional formula of the magnetic field.
You remember
then
the
the
dimensional
dimension-
formula of magnetic field?
No, sir, I checked it from yesterday's notes. Mu naught, I remember.
Mu naught, you remember? Okay, good.
Yes.
But anyway, see, all that is also unnecessary. See, at the end of 2 years, like when you sit in your final exam, it's quite likely that you don't remember, recollect these. But see, it's just magnetic field divided by mu naught. Things cannot get easier than this. We know magnetic field of long solenoid is mu naught Ni. You could have used this formula. Then magnetic field by mu naught will have same dimensions as Ni. That's also H should have same dimensions as Ni. N is number of turns per unit length. So that is L inverse. I is current. That's all. This is the answer, and none of you gave the correct answer. I don't know what complications you all made. If you want, you divide magnetic field mu naught and see this is what you should get. Whatever way you did, do it that way and check why did none of you get correct answers. It's just field divided by mu naught, and every formula of magnetic field we discussed till now involves mu naught. So it's very easy to find the dimensions of B by mu naught. And the
Sir,
unit
I
will be
got
ampere per meter. Okay.
Yeah, sir, even I got it.
Right. So what is magnetizing intensity? Basically, it refers to how strongly we are trying to magnetize something. So it's something which depends on the external field that we applied. Okay, and it is defined as H is equal to B external divided by mu naught. Okay, now what happens when you apply an external field? An internal field gets developed, because as I said, we have not talked about magnets yet, but you can see what happens in the dipoles. The dipoles all get aligned in a particular direction. When we talked about dielectrics, we discussed this. There is an internal field which gets developed. And in electrostatics, the internal field opposes the external field. Fine. The strength of this internal field, of course, it depends on material, but it depends on the alignment as well. Okay. And what dictates the alignment? External field dictates the alignment. So internal field should be proportional to external field. Stronger the external field, better the alignment, stronger the internal field. That's the logic. Okay. So when we apply an external field, an internal field gets produced inside the material. Okay. So B external gives rise to B internal, that is an internal magnetic field inside the material. Okay. Then we define a quantity called intensity of magnetization. Okay. That is B internal, the internal magnetic field divided by mu naught. This is denoted by the symbol I with a bar on it. It's a vector quantity. This is called intensity of magnetization. Means how strongly the material has been magnetized. Okay. And how strongly it has been magnetized will be given by how strong an internal field it created. Okay. So B internal divided by mu naught. It will have the same units and dimensions as magnetizing intensity. Okay. See, these names are slightly confusing, but there is a clear difference between them. Magnetizing intensity is the intensity with which you are trying to magnetize something. Okay. So it refers to the external field. Intensity of magnetization tells you about how strongly the material has been magnetized. So that depends on internal magnetic field. Are the definitions clear to all of you? Did you understand the difference between magnetizing intensity and intensity of magnetization? If you have any doubt, you can ask.
Sir, so intensity is when it puts the force on the other one, and magnetization is when like it's inside, how much it has
See,
been
the
like
word
magnetized.
intensity is there in both the terms. Okay, but is a little bit of English I can say. Magnetizing intensity. Okay, so it's talking about something which is magnetizing something else. Okay, so it refers to the external field. Intensity of magnetization, it's like polarization. In electrostatics, we learned about something called polarization. Means how well aligned the dipoles are inside the material. Similarly, magnetization refers to how strongly something has been magnetized. Okay, and that depends on the internal magnetic field. Depends on the alignment and other properties of the material. So it depends on the internal magnetic field. Okay, and we understand that internal magnetic field should depend on external magnetic field. Of course, it depends on the medium also, like what kind of material it is, how easy it is for those dipoles to get aligned. It depends on the material, but there should be a direct relation between I and H. Do you all agree with that or not? Does internal field depend on external field or not? At least in electrostatics, do you agree with that?
Yes, sir, it does.
It does. Same thing happens in magnets also. Not exactly the same direction, but there is a relation. You will be able to understand. So generally, the intensity of magnetization is proportional to H, the magnetizing intensity. Okay, or you can say internal field is proportional to external field. And the proportionality constant is called magnetic susceptibility of the material. Okay, it is denoted by the Greek symbol chi, but we'll call it as x for now. So the proportionality constant between I and h is x. So we write I is equal to x times of h. Fine. So this factor depends on the material that we are trying to magnetize. And this is what you need to remember. This is the most important term, I would say, in this chapter. They'll give you this value in the question. Okay. Instead of vacuum, if they are using some other medium in the problem, they'll tell you the susceptibility of the medium. Based on that, you will have to make changes. Okay. We'll relate susceptibility to susceptibility to permeability mu. Okay. Then you will be able to solve. Like in electrostatics, wherever we had epsilon naught, that is permittivity of vacuum, if some other medium is used, we have to use epsilon of that medium. Similarly, in magnetism, in whichever formula we used mu naught, if some other medium is present, we have to use mu permeability of that particular medium, and that depends on susceptibility. Okay, you learn how. Fine. So tell me the SI unit and dimensional formula of susceptibility, magnetic susceptibility. From this formula itself, you can tell. This is the only formula we have involving susceptibility. Why is it taking so long?
Is it dimension?
Yes, it is dimensionless because I and H have the same dimensions. Then whatever is there in between them should be dimensionless. Otherwise, the equation will become invalid. Okay. So no units, no dimensions. It will just be a number. Okay. I cannot say exactly the same, but it is somewhat like dielectric constant. Dielectric constant is also just a number, right? No units, no dimensions. Same thing here. But this is not exactly dielectric constant. I mean, this is not analogous to dielectric constant. It's somewhat like that. Okay, fine. Now I is x times of h. I is nothing but internal magnetic field divided by mu naught. That is susceptibility multiplied with external magnetic field divided by mu naught. Mu naught cancels. So you can say the internal magnetic field developed inside a material is x multiplied with the external magnetic field that you set up. Okay. These are vector quantities. Now, inside the material, like go back to this case itself, let's talk about electric field only. We created an external electric field. That electric field will be passing through the material also. And in addition to that, there is an internal electric field. So how do we write the net electric field in the material? It will be the sum of external plus internal magnetic fields. Is this correct or not? Inside the material, both fields will be there, external field as well as internal field. So the net field will be the vector sum of these two. If they are in the same direction, you add them. If they are in opposite direction, you subtract them. But as vectors, this is how we write. Do you all agree with this or not?
Yes.
Right. And B internal is x times of B external. So we can write this as net magnetic field in a material is 1 plus x times the external magnetic field. Okay. Can one of you tell me the basic formula for dielectric constant in a material? How is dielectric constant defined?
Epsilon in the medium by epsilon in vacuum.
No. It becomes that. But like you are saying, dielectric constant is the relative permittivity. That's correct only. It becomes that. But in terms of electric field, how did we define dielectric constant? Okay, quick revision. You consider a dielectric or an insulator. Suppose you set up an external field. Let's say external field is some 20 volts per meter. Okay. And assume it generates an internal field of 5 volts per meter. In insulators, the internal field won't be strong enough to cancel the external field. Internal field will always be weaker than external field. Okay, insulators or dielectrics. Okay, external field is 20 to the right. Internal field is 5 to the left. What is the net field in the material? Anyone? External field 20 to the right. Internal field 5 to the left. How much is the net field?
15 volts per meter to the right.
Net field will be 15 volts per meter, and it's in the same direction as external field. Okay. Dielectric constant of any material is nothing but the ratio of external field to the net field. Or in fact, the basic definition that we wrote is something like this. This net field inside the material, we take it as external field divided by the constant. That constant is what we called dielectric constant. Okay, so in this case, for this material, it becomes external field was 20, net field is 15. 20 by 15, 4 by 3 is like 1.33. That's the dielectric constant of this material. But remember the basic definition. This is how we define it. Net field is external field divided by K. Okay, we'll do the same in magnetism now. Now we have the formula involving net field and external field. So their ratio is what we call relative permeability. Okay, K, dielectric constant, is relative permittivity. Okay, you can write it as epsilon R, and it's defined as external field, magnitude of external field divided by net field. Okay, that is in electrostatics. Similarly, in magnetism, you can take that ratio, B external divided by B net. What does this become? From this formula, what is B external divided by B net?
1 by 1.
1 by 1 plus x. We define it as 1 by mu r, inverse of relative permeability. So basically, relative permeability of a medium is 1 plus x. And that you can write as permeability divided by that of vacuum. So this is how susceptibility is related to permeability of the medium. So as I said, in questions, they'll mention the susceptibility value. From that, you can tell what is the permeability of the medium, and you can use it in all the formulas that we discussed till now. Wherever mu naught is involved, if some other medium is present, you substitute mu of that medium like this. Okay. If they don't want to trouble you much, they'll give you mu of the medium directly, or they'll give you mu r, relative permeability, directly. If they want to check your knowledge of magnetism and matter also, they'll talk about susceptibility. Okay, so let's quickly go through this once again. To magnetize a material, you just need to put it in an external magnetic field. Okay, the external magnetic field divided by mu naught, that term is what we call as magnetizing intensity. And when you put it in an external field, it gives rise to an internal field. Internal field divided by mu naught is called intensity of magnetization. Okay, so I, which depends on internal field, is proportional to H, which depends on external field. Okay, that proportionality constant between I and H, or between the internal and external fields, is what we call as susceptibility. Okay, the name itself tells you the meaning. Susceptible means what? How easy it is to modify that thing or make it do what we want. That is what is susceptible. So basically if X is a high value, internal field will be a high value. Okay, so if the material has high susceptibility, it can easily be magnetized, or it can be made a very strong magnet. Okay. But remember, susceptibility is not directly similar to, it's not directly analogous to dielectric constant. It's not relative permeability. So when you take net field is external field plus internal field, vector sum. So you can write net field is 1 plus x times the external field. That 1 by 1 plus x is what we call as 1 by mu. So mu becomes 1 plus x. Okay. Now let us discuss the types of materials, types of magnetic materials. First, diamagnetic material, or we will basically discuss this property called diamagnetism. So one of you were saying something about diamagnetic materials earlier. Can you repeat that?
For a material to be diamagnetic, it needs to have no unpaired electrons.
Okay, if there are no unpaired electrons, we call the material diamagnetic. Correct. If, okay, there are no unpaired electrons, means all electrons are paired. Okay, and all electrons are paired at the atomic level itself. Okay, if all electrons are paired inside the atom, that means every electron has another electron cancelling its magnetic field. It means atoms of such materials don't exhibit dipole moment. Okay, individual atoms of the material don't behave as magnetic dipoles. Such materials are called diamagnetic materials. Now, if individual atoms themselves are not behaving as dipoles, there is no question of the material behaving as a magnet. Okay, so diamagnetic materials, normally they don't exhibit any magnetism. Okay, you take them near another magnet, or you take them, okay, not another magnet, because that other magnet will create a field. So let's not talk about another magnet, but you take them near iron and all, you won't see any attraction or repulsion happening. Okay, so when there is no external field, when the external field is zero, internal field naturally will be zero, and the material does not produce any magnetism at all. Okay, there are atoms, there are electrons, but the field produced by each electron is cancelled by the field produced by other electrons in that atom itself. So at the atomic level itself, they are cancelled. Fine. Now suppose this kind of a material is placed in an external field, non-zero external field. Okay, listen to this carefully. Assume we switch on an external magnetic field towards right. Can any of you guess what happens inside the material? Some of you may be knowing the answer already. You can tell. Or if you can guess, you guess. At the atomic level, there are no dipoles. Okay, so inside this material, there are no dipoles basically. What happens when we switch on an external field to the right? Okay. See, this is not like insulators. In insulators, the molecules are already polarized, or even if the molecules are non-polar, the electric field we apply will polarize them. And you can tell dipole aligns in the direction of external field. In magnetism, there are some other factors that come into play. Okay. Exact reason you will learn in the next chapter. Fine. You need to know something called Faraday's law. Some of you may be knowing, but once you learn Faraday's laws, you'll be able to explain why this happens. But what happens when we switch on an external field around a diamagnetic substance is, you will see internal dipoles developing in a direction opposite to the external field. Okay, they are not aligned in the same direction as external field, they are aligned opposite to the external field. Why this happens, you will learn in the next chapter, as I said. Okay. Those of you who are aware of Faraday's law, not Faraday's law, Lenz's law actually. Those of you who are aware of that, you can get some idea. Now, electron revolving in an orbit is like a current carrying coil. When you switch on a magnetic field, it produces, before the magnetic field was switched on, the flux through that coil is 0. But when you switch on an external magnetic field, the flux becomes non-zero, means flux is changing. If flux is changing, EMF will be induced, the current will be disturbed, means the revolution of the electron will be disturbed. Some electrons will slow down, some electrons will speed up. It results in an opposing magnetic field like this. Okay, those of you who read or studied Faraday's law, Lenz's law, you'll be knowing induced EMF tries to oppose the change in flux. Now what we did, we switched on a magnetic field towards right, external magnetic field. Earlier it was not there. Now we switched it on and it is towards right. Then internal magnetic field will oppose that. Okay, it will be towards left. So effectively what will happen? An internal magnetic field which is opposite to the external magnetic field gets generated. Okay, dipoles are aligned to the left. The magnetic field will also be to the left. This is what happens in a diamagnetic substance when we place it in an external magnetic field. Okay, why exactly it gets generated in the opposite direction, we'll discuss in detail in the next chapter. Okay, now if internal field is opposite to external field, let's say external field is some 2 Tesla, internal field is some say 0.8 Tesla backward, then tell me, any one of you, how much is the net field? Isha, you tell me, how much will the net field be? External is 2 Tesla to the right, internal is 0.8 Tesla to the left. Okay, Manasa, how much will the net field be?
So 2.8.
See, 2 is in the forward direction, 0.8 is in the backward direction. Why will it?
1.2.
Correct. It will be 1.2 Tesla. So see, actual formula as a vector, if you want to write, you should write B external plus B internal. This is the vector formula. B external is 2 I cap. B internal is minus 0.8 I cap. Okay. Then it effectively becomes 1.2 I cap Tesla. Okay. So magnitude wise, you'll have to subtract them. Vectorially, we are adding them, but final magnitude, if you want, the magnitudes will have to be subtracted. So the net field will be weaker than the external field. What kind of material are we discussing about? Diamagnetic. So in diamagnetic materials, the net field will be weaker than the external field. Okay. Now we can even draw the magnetic field lines if we want. Inside the material, the field is weak. Okay. Now, how do field lines show where the field is strong and where the field is weak? Anyone? How can you get an idea of strength of the field from field lines?
Density of the lines.
Density of field lines, how close they are. Okay. So suppose this is the external field. Close to the material, the field line should be far from each other or inside the material. Basically, this is what happens. The material weakens the magnetic field. Okay. So near the material, inside the material or near the material, the field lines will be far from each other. The field strength decreases. Okay. Or I think it will be even better if we draw these also properly like that. Okay. So B net. Field lines always represent net field, whether it is electric or magnetic, they represent the net field. B net, its magnitude is less than B external. Okay, so we show the field lines moving away from each other. Okay, now let us discuss about susceptibility. Of diamagnetic substance. How did we define susceptibility?
So it is like a factor to how much extent material can be magnetized.
It is the proportionality constant between the internal field and the external field. Okay. Now see, internal field here is opposite to the external field. Since these two, this is in the minus I cap direction, this is in the plus I cap direction. Okay. Or to properly indicate that internal field is opposite to external field, susceptibility of a diamagnetic substance must be negative. Okay, it is less than 0. Very important. Diamagnetic substances have negative susceptibility values. Okay, and see, where did we get that 1 plus x? Yeah, we got B net is equal to 1 plus x times of B external. Now in magnets also, in diamagnetic materials, the internal field won't be strong enough to cancel the external field. Okay, so net field won't become 0. In fact, net field will have the same direction as the external field. External field and net field will be in the same direction. If external field is I cap, in the I cap direction, the net field will also be in the I cap direction. They both have to be in the same direction. Okay. Now, if net field and external field have to be in the same direction, 1 plus x should be positive. Worst case, 0. Suppose the internal field cancels the external field, then the worst case it becomes 0. But it can never be negative. Net field will never be opposite to external field. Okay. So 1 plus x greater than or equal to 0. What does that tell you about x? X should be greater than or equal to? Just send the one that side. It becomes -1. So -1 less than or equal to susceptibility less than or equal to, okay, definitely less than 0, you can say. It has to be negative for diamagnetic substances. So it all arises from the fact, the negative value arises from the fact that internal field opposes the external field. X is the proportionality constant between internal and external fields. No, if you want them to be in opposite directions, then this has to be a negative term. Okay, so susceptibility of diamagnetic substances will be negative, but it cannot be less than -1. Why it cannot be less than -1? If susceptibility is less than -1, net field will be opposite to external field. That never happens. Okay, so it has to be between 0 and -1. Now you all tell me from this equation, if susceptibility is -1, how much is the net field?
Zero.
If susceptibility is
0, sir.
-1, the net magnetic field in the material becomes 0. Means the material cancels the magnetic field. Okay. If susceptibility is -1, B net becomes 0. This is something like what conductors do to an electric field. When you place a conductor in an external field, the charge redistribution happens in such a way that the conductor cancels the external field. Net field in conductor will become 0. Okay. So if that happens in magnetism, we call such materials as, do any of you know the name? Materials which totally cancel the magnetic field. They're called superconductors. Okay. So basically superconductors belong to diamagnetic substances. Okay. And they are diamagnetic substances whose susceptibility is -1. So if you switch on an external magnetic field, The superconductor completely cancels it and makes the net field 0. Okay, but these are very rare. Fine. Is diamagnetism clear to all of you? As you said, these are materials which don't have any unpaired electrons. Means all the electrons are paired at the atomic level itself. So individual atoms don't behave as dipoles. If individual atoms don't behave as dipoles, the object as a whole also won't behave as a dipole. It means it won't behave as a magnet. Okay, but when you place it in an external field, okay, here we took the example external field towards right. It generates an internal field opposite to the external field. Okay, and because internal field is opposite to external field, the susceptibility will be negative. First point. And we know net field is 1 plus x times of external field. The net field in diamagnetic substance will never be opposite to the external field. It will either cancel it exactly, and I mean, it will either be 0 or be in the same direction as external field, but net field will never be opposite. Okay, so 1 plus x has to be greater than or equal to 0. From there, you get the fact that susceptibility of diamagnetic substance should be between 0 and -1. Okay, if it is -1, it means the net field is becoming 0. Such materials are called superconductors. Is it clear to all of you?
Sir, can you tell like what materials are superconductors?
I'll find out and tell. I don't remember.
Sir, or they said like when we keep a magnet in liquid nitrogen, it converts into superconductors.
Actually, there is active research going on. They are trying to develop materials which show this property of superconductivity at room temperature. At room temperature, it does not happen usually. Okay, so there is research going on. I'll find out and tell you which materials exactly behave and under which conditions they behave. Yeah.
Sir, so can we make a normal material which is a conductor into a superconductor? Does that happen?
Okay, that I don't think. No, I don't think all materials can be converted to superconductors. No.
Yeah, but
They
there are
should-
cases like that, right?
the material should exhibit some properties which will enable it to become a superconductor.
Oh, okay.
Okay. Yeah, I'll find out which materials can do that. Okay. Now see, basically what happened here when we switched on the external field, okay, some electrons slow down and some electrons speed up, producing an internal field in the opposite direction. This slowing down of some electrons and speeding up of some electrons happens with every electron, with every material, not just diamagnetic. Okay, so they say that diamagnetism as a property, diamagnetism is seen in every material. Now don't say every material is diamagnetic. Okay, what we mean by diamagnetism being seen in every material is that some electrons slowing down and some electrons speeding up when we switch on an external magnetic field. That happens in other materials also. So all materials exhibit this property called diamagnetism. But if you want to call a material diamagnetic, at the atomic level, there should not be dipoles. Okay, atoms don't exhibit dipole moment. This is what makes the material diamagnetic. Okay. The next type of magnetic materials are paramagnetic. Okay, wait, we need to discuss one more thing also. Dependence of susceptibility on temperature. Tell me, generally, forget about magnetism and all, any material, if you raise its temperature, what happens inside the material?
The atoms get excited.
Basically, atomic and molecular vibrations will increase. Okay, but see, in diamagnetic materials, the atoms were not dipoles in the first place. They didn't exhibit dipole moment of their own. Whatever dipole moment arises due to external field. So in case of diamagnetic substances, the susceptibility is independent of temperature. Okay, so it doesn't depend on molecular vibrations and all, because the internal magnetic field purely arises from the external magnetic field. It's not coming from the own dipole moment of the atoms. Okay, so the susceptibility is found to be independent of temperature. Okay, remember this. Next, paramagnetic substances or paramagnetism. Now, if there are no unpaired electrons, we called it diamagnetic. So if there are unpaired electrons, then it will either be paramagnetic or ferromagnetic. Now tell me, if there are unpaired electrons at the atomic level, does that make the atom a dipole or not?
It does.
It does. See, every electron produces its magnetic field, and all the magnetic fields produced by electrons are not getting cancelled. That is what having unpaired electrons means. Okay, so unpaired electrons are present at the atomic level. That means atoms behave as magnetic dipoles. Okay, so in a paramagnetic substance, normally means when there is no external field switched on, what you will see is something like this. There will be dipoles at the atomic level, but there is no reason why they need to be aligned properly in the same orientation. So they'll all be aligned in random directions like this. Okay, there will be, as I said, millions, billions, trillions of such dipoles inside the object. So suppose we don't switch on any external magnetic field. At the atomic level, there is magnetism. Okay, each arrow represents the dipole moment of an atom. Okay, but they are all randomly mixed or randomly arranged inside the material. So tell me, what will be the net dipole moment of this system? If all the dipoles are randomly arranged, what or how much will the net dipole moment of the system be? Okay, just tell me, will it be zero, non-zero? You have a huge collection of vectors which are randomly aligned. What will be the resultant of all those vectors? It will be zero. Okay, it will be zero. Why will there be alignment or preference to a particular direction? They are randomly aligned. None of them have any preferred direction of alignment. So the net dipole moment will be zero. So when external field is zero, the internal field will also be zero. The material will not behave as a magnet on its own. Okay, at the atomic level, magnetism is there, but the object as a whole has a huge number of atoms. So there are a huge number of dipoles in random alignments. The object as a whole will not exhibit any dipole moment. It will not behave as a magnet. Okay, so when external field is zero, there is no magnetism. Okay. Now, suppose we switch on an external field, let's say to the right. Okay, in diamagnetic materials, when we switch on an external field to the right, what happened? In diamagnetic, when we switched on an external field to the right, what happened?
Internal field was developed.
Internal field
Was developed towards the left.
was developed towards left. The dipoles got aligned to the left. In paramagnetism or in paramagnetic materials, the dipoles tend to get aligned in the same direction as the external field. Okay. See, each arrow head represents a north pole, tail represents the south pole. So they prefer to be aligned. I mean, they tend to get aligned in the direction of external field. Effectively, what will happen? This will be the north pole of the object, and this will be the south pole. Internal magnetic field will be in the same direction as the external magnetic field. Inside a magnet, the field is from south to north. Okay. So you will see an internal field in the same direction as external field developing. It's exactly the reverse of what happens in diamagnetic. Okay. Now, suppose external field is some, let's say 1.5 Tesla, and the internal field developed is some 0.4 Tesla. Tell me, how much is the net field? External field 1.5 Tesla, internal 0.4 Tesla. How much will the net field be?
1.9 Tesla, sir.
Since they are in the same direction, they'll get added. Okay. The vector formula is this: B external vector plus B internal vector. This time both of them are in the I cap direction. Okay. So the net field will simply be 1.9 Tesla, and it will have the same direction as the external field. Okay. So external, internal, and also net field, they all have the same direction in paramagnetic substances. And and net field 1.9 Tesla is stronger than the external field. So if you want to draw field lines, you should show them coming closer near the material. Okay, that will be the field line pattern around a paramagnetic substance. Okay. We didn't talk about north and south in the previous case. It's obvious anyway, dipoles are to the left. So this end behaves as a north pole. The other end behaves as the south pole. Okay. But in case of paramagnetism, paramagnetic materials, you'll get north pole aligned in the direction of external field, south pole opposite to external field. Okay. Next, we need to talk about susceptibility of this kind of material. Basically, it's the proportionality constant between internal field and external field. We know that B internal is X times of B external. Okay. Now, B internal and B external are in the same direction now. For two vectors to be in the same direction, the proportionality constant between them should be positive or negative?
Positive.
Positive. So susceptibility of paramagnetic substances is positive. Fine. Greater than 0. They say it's a small positive value. Why small positive? The internal field will not be that strong. Okay, compared to the external field. It won't even be as strong as the external field. Okay. It'll just be some small internal field getting created in the same direction as external field. So the net field will just be slightly greater than external field. Or you can say B internal is just a fraction of B external. So susceptibility of paramagnetic substances is a fractional. Usually it will be less than 1 only, small number. Okay, but it's positive. Why is it positive? Because internal field, external field should be in the same direction. Okay. Next, what happens to this susceptibility when we change the temperature of the material? Now this time in paramagnetic, at the atomic level itself, there were dipoles. Atoms behave as dipoles, right? When you put it in an external field, basically these dipoles tend to get aligned in the direction of external field. There's no perfect alignment, but they tend to tilt towards the direction of external field. Now, when you increase the temperature, that alignment gets disturbed. Now you see, they're all not perfectly aligned. They are still in random directions only, but tilted towards the direction of external field. Not like diamagnetic. In diamagnetic, they were all strictly opposite to external field. Okay, but here it's not exactly in the same direction as the external field. There is still some tilt. Okay, so when you raise temperature, what happens? The dipole alignment gets disturbed. And if dipole alignment gets disturbed, internal field becomes weaker. Internal field becomes weaker means susceptibility decreases with temperature. Okay, for the same external field, internal field will be weaker if you raise the temperature. So susceptibility of paramagnetic substances, it is actually inversely proportional to absolute temperature. Temperature has to be in Kelvin. Okay, then it is found to be inversely proportional. Okay, the reason being temperature increase disturbs the alignment. That means it weakens the internal field. That means susceptibility decreases. Okay, so susceptibility of paramagnetic is inversely proportional to temperature. Like quite frequently they ask questions based on this. They'll just give two temperatures and ask what is the susceptibility ratio, or they'll give susceptibility at one temperature and they'll ask susceptibility at another temperature. Easy to explain or easy to calculate. Okay, so that is about paramagnetic. So tell me, what is the difference between diamagnetic materials and paramagnetic materials in the first place? Like before applying external field and all, as in the material itself, what is the difference between dia and para? Pradyun, can you answer? At the atomic level, what is the difference between dia and para? You can unmute and tell. Or okay, fine. Yeah, you are saying it's about paired
Between
unpaired.
the paired and unpaired electrons in diamagnetic, there are paired electrons. In paramagnetic, there is one lone electron.
Okay, in diamagnetic, all electrons are paired, so the atoms don't behave as dipoles on their own. In paramagnetic, there are some unpaired electrons at the atomic level itself, so atoms behave as dipoles. But normally, those dipoles will be aligned in random orientation. So as such, the material doesn't exhibit magnetism. But when we switch on an external field, paramagnetic material starts behaving as a magnet. Okay, and it adds to the external field. Internal field adds to the external field. Net field will be even stronger. So positive susceptibility, and it is inversely proportional to temperature. Okay. Try to answer this. Suppose there is a diamagnetic material and you bring a strong magnet close to it. When you bring a magnet near a diamagnetic material, what happens between them? Will they attract, repel, or nothing happens? Think carefully and answer. Don't be in a hurry. Will they attract, repel, or nothing happens? Or whether they attract or repel depends on which pole of the magnet is brought closer to it. Okay, think carefully and answer. I got one answer as nothing happens. Can you explain why you think nothing happens?
Because there is no like
There is
polarization. There's no polarization inside the material, so
But-
there is no concept of south or north.
See, as such, there is no polarization. Okay. But
So will it just repel the material? Will it just repel the magnet? Because
Okay.
it only has electrons and not, it does not have a dipole, so it will not be able to attract.
why should electrons be repelled by magnets?
No, as in the sense like since it's a double electron species, shouldn't it only have the capability of attracting? It will not have a positive charge even if it uses the lone pair.
No, I didn't understand. See,
Sir, under the
there
case
all
it has-
electrons. Yeah. Tell me.
Sir, under the case it has 2 electrons which are
Okay.
paired.
Huh.
It should not even unless it loses those electrons, it should not be able to gain a positive charge. Hence, it should only
No, that is my question. How is charge coming into the picture? Like, do you say positive charges will get attracted to magnets or repelled by magnets?
no.
Nothing like that, no? Okay. Listen, all of you. As such, the material is not a magnet. Diamagnetic material is not a magnet, but we brought another magnet close to it. Magnets produce magnetic field. That's the only thing they do. Okay. Suppose this magnet had its north pole at this end and south pole at the other end. Now, the field produced by a magnet, the field lines, will be out of the north pole like this. For the diamagnetic substance, this becomes the external field. Okay, the field produced by the magnet is the external field for the diamagnetic substance. Yes or no? It's coming from an external source only, no? So that will be the external field. So now, effectively what we have done is, we have placed the diamagnetic substance in an external field. What does it do to the diamagnetic substance? When you place diamagnetic in external field, what happens?
A weaker internal field gets developed inside the object.
An opposite internal field gets developed. Okay. So here, external field is sort of to the right. Then internal field will be to the left. If internal field is to the left, it means this end of the diamagnetic material becomes the north pole and this becomes the south pole. Now tell me what should happen. Should it get repelled by the magnet or attracted by it? It will get repelled. Are you all convinced? Did you all understand?
So, but if
Can you
you
explain once?
Okay. This magnet, which we brought near the diamagnetic substance, produces a magnetic field. Every magnet produces a magnetic field. Okay. I assumed this magnet's north pole was nearer to the diamagnetic substance. Now, if north pole is nearer, field lines generally come out of the north pole. Outside the magnet, field lines go from north to south, means they originate from north and go to south. I should not use the word originate actually. Field lines don't end anywhere, okay, or start from anywhere. They are circular, not circular. They are closed loops. So basically, the magnetic field produced by a bar magnet, it would be like this. Inside it is from south to north. Outside, they go from north to south. Okay, they complete the loop. So that is the field produced by this magnet. Now, this field produced by the magnet becomes the external field for the substance. So it's like the diamagnetic substance is now in the presence of an external field, which is more or less directed to the right. If the external field is to the right, the internal field will be to the left, which means inside the diamagnetic material, the left end will behave as the north pole and right end will behave as the south pole. And since north and north are closer, repulsive force will be stronger. Of course, see, you think in terms of field lines. Field lines are to the right, kind of to the right. Okay. North pole is like positive charge. Positive charge experiences a force in the same direction as field. So the north pole experiences a force to the right like this. South pole is like negative charge. Negative charge experiences force opposite to the field. So on the south pole, there will be a force like this, but this will be stronger. Why? Because it is closer to the magnet. Okay, so effectively, the net force will be a repulsive force. Is this clear to all of you? Still any questions?
But this repulsion will not be visible to the naked eye.
It will be.
Oh.
It will be. It is significant. Okay. I mean, it depends on how heavy the object. Suppose the substance is too heavy, then the magnetic force may not be able to move it. Okay, but it can be seen in real life. If you take very light objects and usually suspended objects, if you take, that will be the best case. You can avoid friction and all if you suspend material. What am I saying? If you suspend objects, you can avoid the effects of friction and all. In that case, it can be seen. Now, even if the south pole had been closer, you will still see repulsion. See, basically what happens, suppose the south pole of the bar magnet is closer to the diamagnetic material. Now, at the south pole, what happens? The field lines will be entering into the magnet. So this time the external field is to the left. If external field is to the left, internal field will be to the right. If internal field is to the right, then the north pole will be developed here, south pole will be developed here, south-south, repulsion will be stronger, it will still get repelled. Okay, so diamagnetic substances are repelled by magnets or repelled by magnetic fields, you can say. They tend to move from a region of, see, this is a region of strong magnetic field, okay, closer to the magnet, no? So the magnetic field is strong here. And this is a region of, or anywhere ahead, is a region of weak magnetic field. And the diamagnetic substance tends to go from a region of strong to region. It is experiencing repulsion that way, no, towards the weak field. Okay, so we can say that diamagnetic materials tend to move from a region of strong magnetic field to a region of weak magnetic field. Okay, this naturally creates another question. What if the diamagnetic substance is in a uniform external field? Now, if the external field is uniform, internal is opposite to external, you will see a north pole developing here and a south pole developing here. Okay, I took external field to the right, so internal will be to the left. This is how it gets created. North pole, as I said, is like positive charge. It experiences a force in the same direction as the field. South pole is like negative charge. It experiences a force opposite to the field. Since the field strength is same everywhere, okay, the external field is uniform, no? Since the external field is uniform, this force and this force will have the same magnitude, then the net force will be 0. Okay, but the question I asked was a bar magnet being brought closer to the diamagnetic substance. Bar magnets don't create uniform fields. Bar magnet is basically a magnet, it doesn't create a uniform field. Okay, closer to the magnet, field will be strong, farther from the magnet, field will be weak. So the diamagnetic material gets repelled. Okay, is it clear to all of you? Any questions?
Can you scroll down a bit once? The last statement.
This one.
Yes, sir. Yes.
Others, any doubts? Fine. So next class we'll discuss about ferromagnetic materials, the property of ferromagnetism, and then we'll discuss some basic properties of bar magnets. Okay. Simple chapter only, but the relation between susceptibility and relative permeability, that's the most important thing. 1 plus x becomes mu r, relative permeability. That is permeability of the medium divided by that of vacuum. Okay, I would say this is the most important takeaway from this chapter. This will be used in other chapters. Okay. Fine. So I'll send the notes to all of you. Go through those definitions: magnetizing intensity, intensity of magnetization, and how susceptibility relates them. Do that derivation once on your own for dia-para. You'll understand. Next class we'll discuss ferromagnetism, and we'll close this chapter. Okay. Thank you all.